So, you going? Okay. So today we're going to be talking about electric fields and the movement of charge through both insulators and conductors. So to start off, we just want to define some key terms for you guys. So the things I think that you should know are that charge is an intrinsic property of matter, and that it causes it to experience a force when it's placed in a type of electromagnetic field. Current is basically just the flow of electric charge. Electric fields are an alteration in space-time in which changes have the potential to exert forces on each other. Okay. So off of that,
you guys grade the groups as a whole.
Okay. Off of that, any electric charge creates an electric field, and this kind of extends outward and permeates all of space. If a second electric charge is placed on this field, it will feel a force as a result. So I'll just draw that for you. So you have a positive charge and a negative charge.
Puts the electric field and always goes out from the positive, it goes around, and then it always goes into the negative. In this direction, arrows always from the plus to the minus, as if the plus has more and it wants to give some to the minus.
So the next thing we're going to talk about are the difference between insulators and conductors. So essentially, insulators are a type of material or a medium that doesn't allow charged particles to flow freely. This makes it really difficult to conduct an electric current whatsoever. But conductors, on the other hand, are materials that allow charged particles to flow at very great ease. So, more like the sea of electrons.
Yeah, so the reason why certain conductors work, such as metals, is because they have just this sea of electrons in them. You know, the electrons are loosely bound, so it's like an ocean. You can send waves through it really easily. But on the other hand, insulators such as rubber or wood or whatever do not have this aspect, so a current cannot be sent through it.
Alright, so now we have a demonstration for you guys.
So we have some insulators right here. We have some string, we have a rubber band, and then we have some iron and copper. And then we're going to run it through our circuit. And you can tell if the material right here is an insulator or a conductor by whether or not the steel wool burns. So string, test one. Think about what you think it's going to do. Oh, what do you know? Nothing happens. String is an insulator. Let's try to get in with another proposed insulator, which is the rubber band. What do you think is going to happen? Possibly the same effect because it is also an insulator. So, ready? 3, 2, 1. And nothing happens because it's an insulator. However, on the other hand, if you take a conductor such as copper, copper is a conductor because it has a sea of electrons, allows charge to flow through freely. Should I go zap myself? Are you ready for this work?
Yeah. Try making it. You want to see it?
Making it smaller. It's hot. I can feel it. It's definitely hot.
There we go.
Look at that.
Yeah.
Ooh, it's hot. So we created a short circuit, right? Because the charge was able to flow too quickly through the steel wool without any resistance. So let's try it again with another proposed conductor. Let's try it with iron. Sam, if you would.
Absolutely.
Yeah.
Oh, yeah.
So we're going to try put our steel wool back on here. Okay, let's connect that last. Ready, let's see what happens.
3, 2, 1. Oh, it's definitely smoking.
Yeah, it's smoking. Oh,
There we go. Okay. Took it a little while longer than the other one, but
Yep.
got there
And what do you know? The conductor works again. So, whether or not the substance is an inductor, as an insulator or conductor, can be seen through the burning of the steel wool, as we saw. If it burns, a short circuit has been created, meaning the charge is low with little or no resistance and much ease to the current. If it doesn't burn, the insulator is providing too much resistance for the charges to pass through.